All right. So I'll be speaking about SRG, e-ROSITA All Sky Survey. I'm pretty sure that almost nobody, probably except for 1 or 2 persons sitting in this room, knows about the history of SRG, where it's coming from. Actually, it has a long and turbulent history. It started in 1987 when I was a PhD student. And as a young scientist, I witnessed many developments which was happening there. This was just some historical remark. This was when like the Cold War became softer, and Soviet Union wanted to make more international collaboration in science, which was a very good time. I remember when, as a young person, like, you know, we had a lot of exchange with people from West, from China, from the US. And so Soviet Union offered, or Academy of Sciences or Space Agency, whatever it was, offered to international community to suggest proposed payload for a big space observatory in high energies, in X-rays. And it was, in the end, it was something like this. I witnessed how, and also took part as a young scientist, how the payload was selected. And there was this very, you know, interesting looking satellite was developed, and it was built actually. We called it, as a joke, we called it a Christmas tree, because it had like half a dozen of instruments with participation of more than like a dozen, probably 15 countries from everywhere: US, Israel, Europe, Turkey, and Eastern Europe, Western Europe. Everybody was there, and it has everything. It would have, if it was launched, it would have the first X-ray polarimeter on a proper satellite. It would have first Bragg spectrometer on the proper satellite, and it would have first big grazing incidence telescope with big collecting area. It was almost built, but not quite. Unfortunately, well, this was the times when the Soviet Union had very turbulent events, and so it was not finished. And in 2001, it was cancelled. And the project science leader of the SRG was Rashid Sunayev, who was at the time my PhD advisor in 1987. And but then, like, we felt it was, you know, it was closed, it was cancelled, but still, like, something was unfinished. We had this feeling, and thanks to the efforts of Rashid and a few other people in Soviet Union, in Russia, and also in the West, including Gunther Heisinger, who was at the time was MP director, it was a new mission was born. In 2007, this is an official assignment of all the agreements. The mission was completely different. It had only same name, word gamma stuck. There were gamma ray instruments here. There were no gamma ray instruments here, but the word gamma stuck, so it remained spectrum Röntgen gamma, SRG, also for some bureaucratic reasons. So then the concept of a new observatory was emerged, and it was designed to detect all massive clusters of galaxies in the observable part of the universe. That was the main, what we put on our flag when we were coming to various authorities and space agencies and so on. Right, so it was launched in July 2019 with a Proton launcher in Baikonur facility. At Baikonur facility was a very spectacular launch. A few of us, like German consortium and Russian scientists, we had a chance to go there to the launch site. Actually went twice, because the first time it was delayed, so we had to go the second time. It was launched, and this is what it was like just a few months before launch. It has now 2 instruments, 2 grazing instruments, X-ray telescopes. The soft one, e-ROSITA, which was German built, and just delivered as a whole thing. We call it Russian, Mikhail Pavlinsky Arctic Sea telescope, working in a harder band. It has mirrors which were built in Marshall Space Flight Center. They were, some of them were bought just for money, and some of them were for exchange of data. They have collectively, they have like several hundred X-ray mirrors. So we joked, we said, this is the biggest collection of X-ray mirrors in space. It's probably something like 500. I forgot the exact number. And so it was launched. The plan was to have it at the L2 point. of the Sun-Earth system. It arrived there after a couple of months after the launch, and then after doing instrument verification, calibration, and everything else what you're supposed to do, it started all-sky survey. I'll speak about all-sky survey on the next slide. In December 12th. Well, unfortunately, in February 2022, by request of Max Planck Institute for Extraterrestrial Physics, e-ROSITA telescope was switched to the safe mode. It's important to understand it was not switched off completely. It's a very sophisticated and fairly expensive piece of equipment in space, fully functioning. You don't just leave it like that. Don't switch it off if you have some reasonable mind. But it was put in safe mode when it doesn't register any photons, and so SRG continues to operates in the interest of Arctic Sea telescope for benefit of Russian scientists and American scientists. As I said, still small packages of telemetry are being downlinked every day or from e-ROSITA just to check its status, and then it was switched on a few times once in a while just to make sure that it operates and it's in a perfect operatable condition. So hopefully it will help to convince authorities that, well, it's probably time to switch it back on. Right. So the main component of the science program of SRG is all-sky survey. And the way it is conducted, so telescopes make big circle on the sky, and the axis of this circle is directed towards Earth, Sun approximately. As the Earth moves around the Sun, the plane of the scan moves by approximately 1 degree every day, every 24 hours, so that in 6 months we cover the full sky. And it was designed to be 25 times more sensitive than the previous and the only all-sky survey, which was conducted in X-rays, which was conducted by ROSAT, also built by MPE, Max Planck Institute for Extraterrestrial Physics, in 1991. So right now we completed 4.4 surveys out of 8 all-sky surveys planned. Why 8? There was a careful calculation of sensitivities, so this is what we needed to detect all massive clusters of galaxies in the observable part of the universe, and also 8 surveys made a possibility to study the variability of the sources, which is also an important part of the scientific program, as you see. And because all the scans, they cross in the ecliptic pole, so in the ecliptic pole we have really very deep exposure, like over 100, 150 kiloseconds, although we get confused there from effective confusion. Now, why at all would you want to do all-sky survey in X-rays? You may say, well, everybody doing is all-sky surveys, like optical, there is punch stars. Even in radio, there is now all-sky survey, in infrared, in UV. So we just decided to do it in X-rays, but this is not just that. So X-rays is a primary signature of accretion onto supermassive black hole. And it's one of the 2 most efficient ways to detect clusters of galaxies due to emission of a hot gas, which is massive amounts of a hot gas in clusters of galaxies, as you know. And this is one of the 2. The second is Sunyaev-Zeldovich effect. And then, of course, you build detailed map of the whole sky, which would be 5 to 10 times better than anything what we had before in depth, in angular resolution, in energy resolution. And that would give you, to study diffuse emission in the galaxy, local bubble, various interesting things, which you show in a couple of next slides, and also to do astrophysics of many kinds of objects, cataclysmic variables, stars. As it turned out, stars are a very important contributor to X-ray emission, and exogalactic objects. I'll be talking about I'll give an overview of the results from all-sky survey, but of course you understand, in 30 minutes, I'll be very superficial. So I will show some potential of which data has and mark the directions where we're working and where we're producing results. So a couple of examples. There was this statement here that it's a good way to find clusters of galaxies and supermassive black holes. A couple of examples to support my words. This is an SDSS image, few by few arc minutes. We know that there is a quasar at the redshift of 6.2. You don't see it on SDSS image. You take deeper image, you go to deeper image of Désilis, or you do proprietary observations, and you find a very, very faint source with quite peculiar colors, but you don't see from one band image, you don't see it, which is like, you know, nothing as compared to bright and nice galaxies which is surrounded here. But if you go to X-ray band, this is the image of the same size as is the DSS image. And this quasar is the only source which you see there at all, at the depth of these observations, which is fairly good depth. Clusters of galaxies. This is an example of a cluster of galaxy which is fairly massive, almost 10 to the 15 solar masses, and at the redshift of 0.8, which is quite distant. This is an optical image. I know people who would say, oh, of course, there is a cluster of galaxies. I am not one of those people, but if I look at this image and do a couple of exercises, couple of fits, I would immediately say this is a cluster of galaxies. There is a very clear, sufficiently very bright and extended X-ray source. So this is just to illustrate that it's there is a lot of potential in all sky X-ray surveys. So goals are to produce. Its mainly initial motivation was mainly extragalactic. So the goals are to produce large and uniform samples of supermassive black holes, AGN, quasars, well, galaxies to less extent, clusters of galaxies. And we're talking, when we say samples, we're talking about tens of thousands, millions of objects. Like we have already a couple of million of quasars detected in X-rays. And of course, if you have that with controlled incompleteness, because we know exactly how long we observed every patch in the sky, and we know what sensitivity is, you can do a lot of nice and interesting things. Cosmology, large-scale structure, build of supermassive, growth of supermassive black holes, but also there is a lot of astrophysics like galactic sources. We detect many, like hundreds of thousands, 500,000 stars almost. And, you know, people looking for cataclysmic variables, for emission from millisecond pulsars, etc., etc., etc. So it was planned, I'll just remind, it was planned to perform 8 surveys. Now we have 4 full surveys, and 40% of the sky was covered for the 5th time. Also, I should mention, so this is a German-built, e-ROSITA is a German-built telescope. And I should probably say at the beginning, I'm talking about e-ROSITA. The second telescope, ARTEC-C, is outside the scope of this talk. So it was built in Germany, and it was on the bus, on the satellite, which is built in Russia, and was launched with the Russian rocket. So there was agreement between agencies that the data is divided 50-50 between German consortium, which is led by MPE, and Russian consortium, which is led by Space Research Institute in Moscow. And the division goes along the big circle in galactic coordinates going for the galactic center, Sagittarius A star. Right, so I'll be talking, and we call it like Eastern, being politically correct, we call it Eastern and Western galactic hemispheres. So I'll be talking about Eastern galactic hemisphere. Now, to put it in perspective, this is a diagram of most recent and most significant surveys, wide, narrow, wide angle. This is the area of the survey, like 1 degree, 1,000 degrees. This is full sky, and this is the depth going to 10 to minus 16, even low 10 to minus 17. So of course you would want to get here. You want to cover full sky with a very good, you know, as good as possible sensitivity. Well, this is a dream, of course. In reality, every program has its resources, and you either go deep but narrow, or you go broad and not so deep, relatively shallow. This is the ROSAT, the only all-sky survey which was conducted in the history of X-ray astronomy. So we already now, with collected data, with 4.4 surveys, we are here. We are already 15 times more sensitive, deeper than ROSAT all-sky survey. Also we have significantly better angular resolution and much better energy resolution and energy range. So it's a very significant step forward, and we already make a couple of discoveries. So I mentioned in the beginning that the sky is like there are 2 hemispheres, two consortia, which are responsible for analysis of each of its own hemisphere. But we envisage, like, understanding was, at least among scientists from very beginning, that when needed, of course, we will combine, we do things together. And this is an example of that. It's all sky map. It's a RGB map. Soft is about 0.5 keV, middle energy is about below 1 keV, and high energy hard is above 1 keV slightly. And so this is RGB map of the whole sky in galactic coordinates. And like blue is hard, red is not so hard, and yellow is soft. And no, red is soft, yellow is intermediate hardness. Right. So this is all sky map. What do you see here? We see two very significant large-scale features. One of them, this like a cut through along the galactic plane. This is very easy to understand. This is a distribution of neutral hydrogen in the galactic, in the galaxy, and it all concentrates to the galactic plane, of course. And if you compare this cut through the X-ray image, where we have lower brightness and harder spectra, goes along the galactic plane. The next big feature is this. This is somewhat, it was noticed in Rosat maps. At the time, initially, it was called North Galactic Spur. But now with the e-ROSITA map, we see that it's some kind of bubble. It's very obvious here in the upper is, I'm not an astronomer, I think it's a northern hemisphere, right? And some also in the lower part, in the southern hemisphere. What makes it special? Look at this image. So this is red is Fermi data. It's 1 to 5 GeV emission from Fermi, and blue is the same map as before, but I just removed all the point sources and a bit played with the scale, with color palette, but no Photoshop here. I didn't change any pixel value. So, and then you see that it's e-ROSITA, we call them e-ROSITA bubbles, and e-ROSITA bubbles, they envelope Fermi bubbles. And then actually we see, moreover, we see like here, well, the pointer is not sharp enough, but you see there is a sharp transition here. We see temperature drop there. And this must be a shock. And if you interpret the numbers, temperature change from 200 to 300 electron volts, you get a Mach number of 1.5. So this is a bubble which is expanding with the Mach number of 1.5, which is supersonic in the surrounding ISM. Well, you can compute all the numbers like luminosity, total energy content. So I don't have time to stay too much on this slide, but these are, as well as Fermi bubbles, this is some result of some activity in the central region, the nucleus of the galaxy. Could be supermassive black hole, which was fairly bright, getting close, some fraction of Eddington luminosity for a couple of million years, or could be still marginally a star formation event. It fits, but just marginally, so maybe even doesn't fit, which lasted for 10 million years. Right. So if you look at this map, so apart from these big features, you see the smaller features, but you also see many white points, and these many white points are sources, and some of them are clusters of galaxies. Some of them are stars, X-ray active stars, and some of them are supermassive black holes beyond our galaxy. And so before I move forward, this in the rest of my talk, I'll be talking about point source. Point source is clusters of galaxies and extragalactic component about quasars, AGN galaxies. And this is our collaboration. These are two science working groups, X-ray Catalog and QSOTD, which I chair. So two prominent members of our groups are Rashid Sunayev and Alexei Starobinsky. They help us to keep our bearing so that we don't get, spend too much time on little things. And then, of course, we have young people. Pavel Medvedev is instrumental in doing pipelines for data calibration and source detection, etc. Alexander Meshcherikov he leads a subgroup of machine learning neural networks. Some of the results I'll be showing later are obtained in his group. And this is a group of observers on various telescopes, including Palomar and Keck. And Sergei Sazonov is my deputy in the quasar group. Right. So this is the same image with point sources more obvious. So what we have in 4 sky surveys, we detected 1.5 million X-ray sources at the detection likelihood level exceeding 8, which corresponds to which gives about less than 1% of false sources or false detections. Because when you operate with millions, 100,000 sources, you say, okay, it's a 10,000 false sources in this sample. Who cares? It's just 10,000. It's just less than 1%. It's a joke in a way, but if you work in statistical way, this is how you approach it. There is, thanks to Gaia, we know that there is about over 200,000 stars, which are X-ray active stars in our galaxy. So of this 1.5 million, there are stars. There is more than 1 million of AGN and quasars. There is about 20 to 35,000 clusters of galaxies, depend on the significance threshold you apply. And actually, if you go to the harder band, e-ROSITA is not very good, like beyond 2.3 keV in terms of effective area, but still we have quite a few. We have 5,000 sources, and they are also important for some of the projects which we're doing. I'll tell this later. So you have 1.5 million sources. They are just from the sky. You have their coordinates. So what you can do to make sense out of it, you have to solve few problems. The first problem is identification. You have to find optical counterpart. So without multi-wavelength data, there is not much we can do. But we have to find right optical counterpart, and sometimes, quite often, in the Earth circle, we have more than one optical source. We have to classify, after we found optical or infrared and UV counterpart, we have to classify whether it's star, galaxy, quasar, and then for extragalactic sources, we need to measure redshift. So for this, as we experimented with many, we started this before the launch, of course, we experimented with many ideas, and we found that machine learning algorithms are most efficient. They produce best results as compared with anything else which is published in literature. We also tried some more motivated approaches, but they help to adjust machine learning algorithms, especially random forest algorithms. Here are just a couple of examples. Speaking of classifications, if you choose right coordinates, upper panel is different optical and infrared colors, then red are quasars, green are galaxies, and these are stars. It helps you, plotting such plots helps you to tune machine learning algorithms so that they do it in the most separation of different classes, most efficient way. Of course, there are some overlaps, but you can do it slightly differently. You can plot X-ray to optical ratio against some smartly chosen color, and then you see, like, now stars are here and quasars are here. No, galaxies are here, AGN are here, and this is gray. This is for Lockman hole, by the way. These gray symbols, they are sources of unknown nature. We don't, without optical spectroscopy. But then, of course, you can guess that these are all quasars. And if you find something unidentified here, you would say it's star. But then, of course, you want to measure redshifts. And we do this with machine learning approaches. In particular, these results are produced with random forest algorithm. And this is spectroscopical redshift. It's a test sample, one of the test fields. And this is photometric redshift. And we have very, very good metrics. We always, of course, with photometric redshifts, using broadband photometry, we always have these outliers, but they are fairly controlled here. We have even better results for clusters of galaxies. They are easier because galaxies don't have AGN, which is polluting everything. Right, I think I'm actually pretty much behind my time. And then with this, we get, this is some subsample which contains about 20% of quasars, AGN, which we have. So it's enormous. And we do many things. We try to do luminosity functions. We try to search for population of Compton-Fick AGN. And we're studying variability, many things. I don't have time to talk about this, but this gives you the power of the sample. Let me go further. Clusters of galaxies. at some point, it was like this was, as I said, the design goal was to detect all massive clusters of galaxies in the universe, and we expected to have 50,000 clusters with virial mass of more than 2 × 10⁻14 and 100,000 clusters and groups of galaxies in total. What we have now, these are 4 surveys. So we now still will work with 5 sigma thresholds. We expect to go down to 4 sigma. So if we take this number, we'll have 30,000 in one hemisphere, and there is another 30,000, as Dr. Andrea Merloni, there is another 30,000 on the Western Galactic Hemisphere. So in total, we have 60,000, which is to be compared with 100,000. We get there if we get 4 more surveys. Right, so just pay attention to the right panel. What is shown here, this is just a simple log-n of clusters of galaxies. Blue are those which are known, well, are correlated our cluster catalog with, fairly large number of catalogs of clusters, starting from Planck, Abel, and many others. And so blue is those which I found in one of those catalogs. And whatever it is, orange or yellow, is what was not found in any catalogs. And what you see, of course, the brighter ones were known. But another fact, what you see from here, that about half of the clusters which we find, they were not known before. These are new clusters. And in fact, in doing this, I also include CMB Z effect clusters as well. So, and this is only after 3 surveys. After 4 surveys, we have a bit more, and hopefully after 8 surveys, we will be, most of the clusters which we detect will be previously unknown clusters. As I said in the beginning, there are 2 most efficient methods to find clusters of galaxies. This is a Z effect, Synav-Zildovich effect, and X-ray emission. These are all coming due to the presence of massive amounts of a hot gas. And of course, well, there is a synergy between these 2 methods. You can do many nice things which you combine data, but you also compete who detects more clusters. And here is some summary of the present status. These are clusters in the ACT footprint, where ACT detected 600 clusters. So they are marked here in light blue, in cyan. e-ROSITA detected total e-ROSITA detected 4,000 clusters in the ACT footprint, so almost 2.5, 3 times more. Now, these are those with matches with ACT clusters, and as expected, shown here in red and in blue. Red match with extended sources, and blue matches with the point sources. But these are point sources just because we don't have enough statistics to resolve their spatial extent. And as I said, cyan ones which don't have counterparts in just in time to finish, just to get me out of here. 1, 2, 3. So, and as expected, so Synav-Zildovich effect is more sensitive to more distant, more high redshift galaxies, and X-rays are more sensitive to more nearby galaxies. And this is what we see. We detect all the Z clusters from ACT at lower redshifts, and we detect many more at lower redshifts, and then at higher redshifts, like beyond 1 or 0.8, a Z effect is more efficient. Okay, and then with this, of course, this is not just to detect clusters of galaxies. This is to do cosmology. Well, this is probably a too bold statement at a cosmological conference in front of all these people sitting here, but I still say it. A mass function of dark matter halos is described by some relatively well understood physics. As long as you fix your cosmological model, the rest is not easy, but well understood. Therefore, it can be predicted, and it depends on the cosmological parameters, on the parameters of the universe. X-ray luminosity of an object is, in principle, with many caveats, a proxy to the dark matter halo virial mass of a cluster or dark matter halo mass. Now, in all this combined, like Alexei Vikhlinin did this first, you can actually constrain cosmological parameters. With our size, we have about 50,000 on all sky clusters of galaxies. statistics would be minimal, statistical errors, and will be dominated by systematics. And the main systematics sits here, how to convert X-ray luminosity to the dark matter halo mass. So this is work in progress. It's not that straightforward just to do it right away if you have a cluster of catalog of clusters of galaxies. There is a few minutes. So there is another way to do cosmology with samples of clusters and quasars and AGN. This is the angular spatial distribution, three-dimensional distribution, not only angular distribution. We know universe has structure, which is called large-scale structure, and quasars are sitting in the nodes, and clusters of galaxies are sitting in the nodes of large-scale structure. And we started this some 10 years ago with Gerd Hutze and Rashid Sunayev, making forecasts for e-ROSITA, and then it was later picked up by Sergei Bykov, my PhD student at MPA in Garching. So what we demonstrated at the time, that the size of the e-ROSITA sample of AGN quasars is sufficient to detect BAOs, with some quite reasonable statistical significance to do many interesting things. But of course, this is like in principle, because it depends on the accuracy of redshifts. To do this, ideally, one needs spectroscopic quality redshifts for several million objects, which is probably not reachable right now. But still, what we have now, we have photometric redshifts, and Sergei, this is Sergei Bykov, did simulations. So we know now with real e-ROSITA data and optical multi-wavelength data we have in hands, we know what is the realistic accuracy of the redshifts. And this is, we have the system which is called SRG-Z, machine learning using random forest, and also now neural networks are being attached here too. So using all this, Sergei simulated to what accuracy we can measure various cosmological parameters. And like in the most optimistic case, when we combine AGN and clusters of galaxies and everything goes well, we get rid of all the systematics, then we can measure cosmological parameters with the accuracy between 4 to 5 to 10, 12%. That require significant work, but people do this in astronomical surveys, in optical band, so we should be able to do it as well. Now, my last 2 or 3 slides, last topic for this talk. So the way how the scan is done, we do like we cover 1 degree wide strip on a big circle in 24 hours. And then every next 24 hours, we move, and then we come back in 6 months. So that gives a possibility to study variability of objects on the entire sky with a cadence of 6 months. Of course, in the ecliptic poles, it's much better, but this is a different story. For sources immediately in the ecliptic pole, we get just continuous light curves, which 2 years, 2.5 years long, which is completely different science, power spectra, etc. for brighter sources, right? So, and then when e-ROSITA was operational, every 24 hours, we detected about 3-5 objects which changed their flux by more than factor of 10 as compared to the previous scan. And what was surprising, half of these objects were extragalactic. So actually, we detected massive numbers, massive amounts of extragalactic transients. Of course, another half was galactic, mostly stars, but they were also interesting, but extragalactic was super interesting, and actually tidal disruption events is one of the significant topics which we're working on. So I wouldn't tell about all the studies of variable AGN, but show another slide about tidal disruption events. So we now have a catalog of about 70 plus, so we probably have in total, we have about 100 tidal disruption events. This is comparable or exceeds all the tidal disruption events known before from X-ray, optical, whatever else. It's mostly X-ray and optical. We have a first catalog. We can estimate a mean rate, which is 1 event in 100,000 years per galaxy, but of course it doesn't tell you much. It's like, there is this joke, it's like a mean temperature in a hospital. which doesn't explain anything. What is interesting, we found several events, tidal disruption events, which were associated with neutrino events. And this is, I think this is quite an interesting result. It's about almost final slide. There are a few details about this event. They are all close to getting close to Eddington, Eddington ratios of about 0.5, close to 1 in some cases. And in total, there are 3 tidal disruption events, of which 2 were detected by e-ROSITA aboard SRG. They have very soft spectra. They have all the signatures of tidal disruption events. Oops. They have all the signatures of tidal disruption events, and there are interesting patterns, like neutrinos are usually detected after the main peak of the main outburst. Well, whatever it means, we don't know. Of course, there is always a possibility for chance coincidence. Well, we did various estimates, and they were ranging from, well, we say it's about 3.54 sigma significance at the moment. Okay, so I'm about finished. I'm finished. These are some goals of SRG e-ROSITA. We're moving in these many directions. And yeah, well, producing some results and papers. Thank you.